All right, welcome back. We are in the new machine learning techniques track, starting with a talk by Alex Angermann, who's product manager at Google. Alex, you were also speaker at PAPIs in Valencia 2 years ago, but back then you were at Amazon. Right? Yeah.
So it happens.
Congratulations on the upgrade. No, I'm kidding.
No comment.
No, I think it's great to hear about decentralized machine learning, especially from Google. So yeah, very much looking forward to your talk. And please, everyone, let's welcome Alex on stage again.
All right. Well, thank you everybody for being here. It's day 2 of the conference, and it's afternoon, and it's right after lunch. So these are like formidable barriers. I appreciate everybody who's made it in. So I want to talk to you about machine learning and decentralization. And it's really broad. Like, what does decentralized mean? Well, there's been a lot recently in the news and in the sort of industry medium about things like blockchains and smart contracts and cryptocurrencies. All of these things are based on decentralized approaches. And these are really exciting. I regret to inform you I'm not going to talk about any of that. I actually didn't think I would hear anything about blockchains throughout, but somebody, I think the gentleman from Seed AI did mention them yesterday. So there was a mention. What I want to talk to you about instead is smart devices and edge devices and the ways in which we might consider extending our machine learning capabilities towards these smart devices. And really crucially, what does it mean to run machine learning on devices which may be installed in privacy-sensitive environments, for example, in public spaces or perhaps even in our homes. And this talk has just 3 simple purposes in life. I want to talk about on-device machine learning, and I want to convince you that it's important and it's different. It's not just the same machine learning where you know how to do, just running on slightly different hardware. I want to talk about some specific approaches towards decentralized machine learning. And I want to make you really excited, uncomfortably excited, about a technique called Federated Learning, which is a new and exciting field about applying distributed machine learning techniques to a very heterogeneous fleet of devices out there. So what's a device? Let's just start with that. A device is a lot of things. Perhaps the most intuitive thought you may have is a phone is a kind of device. And phones are definitely the most capable devices out there. There are a lot of them, and they're really personal. There are few things that are as personal of a device as a phone. So a question to the audience, and I promise it's the first and last bit of audience participation. Raise your hand if you remember the last time you were away from your phone for more than, say, a couple hours. Less than half of the room? In a survey from 2015, a quarter of people surveyed said they couldn't remember at all the last time they were away from their device. And something like 79% of people said, well, I'm away from my device for less than 2 hours a day. So these phones are everywhere. They go with us wherever they go. They're just studded with all of these sensors on them. They have location, they have sound, they have ambient light, they have a camera. All of these sensors are there, and through the magic of commercialization of technologies, these sensors are getting better and better, and the phones are getting cheaper and cheaper. And of course, we don't just carry these sensors around. We interact with these phones. We use them to look up information, we use them to communicate, we use them to take photographs. These phones are just incredibly personal. And the way they interact with the physical world and the way we interact with them is this absolute wealth of information. And we should be considerate about how we might use that information and careful as well. Then there's a different kind of device out there, and I call them connected things. Internet of Things is another common name. There are quite a few of them out there, and oftentimes they're all around us without us necessarily knowing they're there, whether it's a security camera, whether it's some kind of an of a traffic sensor, whether it's any kind of ambient environment device that are all around us. There is an estimate that in 2016, so that's already 2 years ago, there were 4 billion consumer devices out there, in addition to many more industrial devices. And these devices are also getting more and more capable. You know, there's often no longer just a single-purpose device that can only do one thing. Now they have many sensors on them, so they can do a lot. And they're gaining their internal compute capabilities as well. And then the last category, robots are kind of this unclear category into which you can lump anything from a vacuum cleaner that knows how to navigate around your home all the way out to a self-driving car. You might call anything that has some autonomous capability to navigate the physical world as a robot. And again, we have quite a few of them out there. We'll have many more. And these devices are also quite capable. So devices, I hope I've persuaded you that we should at least think about how we might use them. Then there is this natural question of what's so different about machine learning on device? Why not just take what we already know, how to do machine learning, and just do the same thing, but on device? This picture here is how most machine learning everywhere is done today in the world. You essentially have this idea of a centralized smart server, and application developers build applications that run on these servers. Users interact with these applications. The interactions generate log data. We can mine the log data for insights, build machine learning models, deploy a better version of the feature. Users go use the feature, generate more data, and you have this virtuous cycle. The more an application gets used, the better the machine learning model that's built on the log data, the smarter the application. And this works really well. I mean, this is the dominant industry pattern. But you know, it's kind of this interesting observation that all the smarts in this picture are in the server land. The device is kind of dumb in this picture. Its only purpose in life is to issue a request, get a response, and presumably some kind of smart response, and then maybe render some UI on top of it and present that UI to the user. And you know, if you just observe that a device is just a very different category of user agent, it's no longer a web browser from 10 years ago, which is what much of this picture really looks like. These devices are more personal, they're more numerous, they're more capable, they're more autonomous. They can do a lot more if only we had a good mechanism to use them. So on-device machine learning, the very first step towards on-device machine learning, and this is becoming quite common, is to take prediction generation and move it out to the device. So instead of having this little brain in the cloud and you make requests into the server to make a prediction, you get prediction, you do something with it, why not take that model and move it out to the device itself? Many devices out there are perfectly capable of running machine learning models and generating predictions. And once they do that, there are tons of benefits to it. You get often you'll get a much lower latency because you no longer have to make a network request to get a prediction. In general, this approach is very network friendly. If you have data caps, these data caps no longer apply if you don't have to make a request out there. In fact, your application can work offline entirely. On-device prediction generation is great for privacy because you don't have to take a piece of data, potentially sensitive piece of data, and send it off the device somewhere else to make a prediction, and then either you have to promise that you won't store that piece of data, or you have to be very careful about guarding that piece of data if you do store it. You get access to all the sensors on the device much more naturally than if you had to take the data from the sensor and again ship it off to some server to process. And the power utilization, which is not to be underestimated in battery-powered devices like, say, a phone, is incredibly more efficient to do prediction on device than to spin up a radio stack, make a request, receive a response, maybe power down the radio stack if you're careful. This could be a difference of a couple of orders of magnitude in battery usage per prediction. So lots of really good stuff here. But there is this question, okay, so we've moved the prediction out to the device. How do we continue making that model better? And there is kind of a natural answer to that, which is anytime we made a prediction on device and we vended that prediction to a user, we have an opportunity to actually generate a new training example because we can predict what the user will do, we can observe what the user has actually done, and record all the context around it. So now we have an example with lots of features, and we have a label. So we can get the training data, and then what do? The most natural thing is to take the training data and send it back to the server where you can aggregate it and build the next version of the machine learning model. And then you can take that model and redistribute it back to the devices. So that closes the loop nicely. It looks a lot like the picture we've seen earlier with machine learning in the server land. But now we have to ask all these questions. What about sensitive device data handling? Just said that on-device predictions are really great for privacy because you don't have to send the data off the device somewhere else. Well, if you take that learning data you generated at the end and send it back to the server, that's not so good for privacy anymore. What about the connectivity constraints? If you have predictions generated in a context where you don't have a lot of connectivity, maybe you're working entirely offline, then your ability to send the training data you've captured back to the server is also similarly constrained. And then there's the question of personalization, and that's a really interesting one. Personalization is a very desirable thing out there. It's a very desirable feature to add to a wide variety of products. And personalization is actually really hard. It's really hard in the context of a global model where you have one model which is the same for everybody or for every device. But you're attempting to get that model to give you personalized results, usually through the mechanism of really clever feature engineering. So you're trying to build out features that can take context of how the model is being used and give back personalized predictions. It definitely works. That's pretty much the only way personalization is done today. But it's not easy. It's much easier to make a global model that works the same for everyone than to make a global model that can return personalized results. So the next step on this journey towards taking machine learning on device is to move the learning process onto device itself, which is actually just shorthand for personalization. That is the most natural way to apply it. The idea is conceptually very simple. Once we've generated training data on device with a label, instead of centralizing the training data and then running a machine learning algorithm on a centralized location, why not keep the data exactly where it is and take the machine learning algorithm and move it to where the data is? Think of it as having many independent models that are each evolving independently. Many devices out there are perfectly capable of running this kind of software. There are many machine learning frameworks, TensorFlow being one of them, that is very happy to run in a wide variety of devices. So this actually works pretty well. And it's an interesting approach for personalization because it presents kind of a radically different way to do it. Instead of trying to be really clever about engineering the features for one global model that will give personalized results, you can start with one global model, and then you can improve the model on each device with data that is tailored or only generated on that device. And so now you have a model that's kind of implicitly personalized in the example space instead of feature space. You also, of course, have a situation where if you have 1 million devices, now you have 1 million models instead of having one global model. So personalization, this kind of personalization is really powerful, but there are also these questions. What about? What about the new user experience? If everybody starts with the same global model and then personalize it, then a new user who shows up gains no benefit at all from the learning done by the other users of the application. They have to start anew. And the rate at which they generate new examples could be quite low. It could take a long time before this model really starts adjusting to that user and becoming personalized for them. And the flip side is for devices that do exist kind of side by side with each other, there is no mechanism for them to benefit from one another. So we all know that models start becoming out of date the second they're created, the world changes. And each device basically has to adjust to the changing world on its own. There is no ability there to benefit from the peers' data to jointly adjust. But you do have all these other benefits, including completely local learning. And since no data leaves the device here, you have these great privacy guarantees. The data just stays on device, period. So the third step, and this is the step that I'm really excited about, and I hope you'll be excited about as well, is take the machine learning and run it across devices. This is the approach known as federated learning. It's quite an active area of research by Google and other collaborators, both academically and at other companies. And I'll talk a little more about how Google uses that in a little bit. But first, the basic idea. Starting with the same setup as we had for personalization, which is we have some kind of a baseline model on the server, and we have mobile devices, and each device has its own local training data. We can send that baseline model out to each device, and then we can train an improvement on each device, just as we did in our previous example. But then, why not take the improvements, only the improvements, think of them as the deltas of the weights in the model, and send them back to a server where they can be averaged together to yield a new model that is actually a combination of the training results on individual devices. And that happens without sending any of the data to the server. So the data never gets centralized, but the updates get aggregated, and then we have a new improved model which we can send back to the devices. And that's not all, because once the model, this improved global model makes it to the device, you can go right back to the local training examples you already captured and update that model with these training examples. So you get a better global model, and then you also get the personalized on device. You don't have to choose, do I want a better global model or do I want personalized models? You can have both. You might say, well, isn't it just like distributed optimization? What's the difference here? And the difference is all in details. The realities of running federated learning out there in the world is that we run an environment that looks nothing like a data center. We have a very large number of devices. You know, instead of having, say, 100 worker nodes in a distributed TensorFlow job in a data center, you might have 10 million devices out there that all have some data, maybe 100 million, maybe 1 billion. These devices have very limited communication. You only get a few rounds at a time, especially if you're trying to be respectful of the device system health and not do things like fire off a bandwidth-intensive operation while the user is watching a movie or doing something to interfere with their experience in any way. You have highly unbalanced data. Some devices will have lots of data, some will have little, some will have none at all. There is no guarantee whatsoever that the data is distributed on these devices in any kind of a way that you can make an assumption on. The only assumption you can make is that there are no assumptions. And the devices are unreliable. They're unreliable in the sense that you cannot rely on them being available and behaving nicely for you to run your distributed optimizations the way you would run in a data center with parameter server. You know, devices go online and offline. People get on airplanes, people drive through tunnels, people do things with their phones that make them slow, and the operating system may start killing processes. Who knows? And then, of course, there is dynamic data availability, which is, you know, if you have devices distributed around the world, and you also have a rules that only devices that are, for example, plugged in and on unmetered connections are participating, well, it's only midnight in some parts of the world. You only get these devices online. You don't get devices from at the same moment from the parts of the world where it's mid-afternoon. So federated learning is different from distributed optimization, but it turns out entirely feasible. Again, this has been a very active area of research. Many papers have been published about federated learning. I encourage you to check them out. I'll have a couple of references, I think, at the end here. It turns out that a lot of these approaches, a lot of these problems can be controlled by having a central server that is smart about which update it receives. So instead of trying to coordinate updates from every client that's ready to give you an update, it very deliberately selects which clients it wants updates on for any given round of model training to control for all these different sources of bias and steering in the wrong directions. So let's talk about privacy for a second. We've had this picture earlier on that each device learned an update, which is just to say, let's call it just weight deltas, and we can send these weight deltas to the server where they can be aggregated together. It's really reasonable to ask, is that really private? Is there any information in these updates that might be sensitive? And the answer is, it depends. For some models, it may not be sensitive at all. For some models, an update by itself can be very revealing about the model usage on a device. I'll give you a simple example. If you have a model that is a keyboard model where you try to learn and predict what is the next word the user is going to type, a model update can be essentially interpreted as a bag of words of everything the user has typed. Incredibly privacy sensitive. And so the question is, could we do better? Is there some way to secure these updates? Before we get there, let's observe some ways in which doing this kind of operation in a federated setting is already better than collecting all the data in a centralized location. One, the updates are ephemeral. You don't need to store these updates. You only need to receive them and process them and throw them away. There is no requirement to store them. That's pretty good. Two, the updates are focused in the sense that a training data example may have all kinds of information, but what makes it to the server has already been through the machine learning process and has been distilled into weight updates. So if there is some sensitive data in the examples that is not used by this particular model, there is no trace of it in the weights. You only get to use the data that is needed for the machine learning model itself. And then, we don't need these updates individually. We only need to compute an aggregate of these updates. That is all that's needed to create a better global model on the server. So wouldn't it be really great if all of these clients can submit updates, and these updates could not be read by the server individually, but could still be aggregated into something that is a global model that can be read? It turns out that there is a very well-established body of literature and an area of computer science that usually goes by the name secure multi-party computation that enables us to do just that. It enables each client to encrypt its update with a key that the server does not have, but in a manner that allows the server to take these updates and run mathematical operations on them, in our case an average, without having to decrypt them. You can average all these updates in their encrypted form. And once you've averaged enough of them, where enough is a configurable parameter, you can reconstruct a decryption key that is only good for decrypting the aggregate. It's absolutely useless for decrypting as an individual update. These updates are completely unreadable by server at any point. And again, they don't even have to be stored. You throw them away as soon as you receive them. So we call that secure aggregation. We have a paper about it out there. It's I would call it a really complex implementation of a really simple and powerful idea from secure multi-party computation. So this is the federated machine learning world, a world where you can run distributed optimization across devices without having to take any data off the devices, and with ability to protect even the updates that leave these devices to be only useful for the task of creating a better model through weight averaging and nothing else. So what are some good applications of that? In some sense, it's any application where you have data that is natively generated on devices. Anytime you have data on devices that is more relevant than the data you have on the server, consider whether it makes more sense to take all that data and ship it to the server and potentially deal with the expense and the difficulty of protecting that data if that data is sensitive or very large, or bring the machine learning process itself to the devices. So privacy is a significant reason why you might consider running the machine learning process on the device itself. Data size is another example where it may just not be feasible to send that data to the server. There is currently this restriction that this is an approach fundamentally for supervised machine learning. And furthermore, you have to be able to get labels on device. And sometimes you can get labels on device explicitly from the user. Oftentimes you can get them implicitly by predicting what the user would do and observing what the user will actually do. Some motivating examples I'll run through really quickly. One is language modeling for mobile keyboards. We've done that at Google for Google Keyboard, and we've published a blog post about it on Google Research Blog. Given a keyboard, it's a place where you can really help a user be more productive on a mobile device by giving them a smarter keyboard that lets you accomplish things quicker. But of course, it's a very privacy-sensitive place to play in. And so we've done models in Google keyboards that run on many, many devices out there today in the real world to help users get things done without taking the data off the device. Voice recognition is a similar category. Anytime you have really hypersensitive personal data, medical data is an example, and there's been some really great talks in the last couple of days about applications of medical data. If you have a device that has medical data on it, federated learning is a fantastic approach to making something with that data without going through this whole process of trying to get all the data into one place and then protecting it and incurring this enormous liability of having this personal data. And then anytime you have a model that wants to incorporate physical context, anything a device sensor can do for you, or device virtual state, for example, what apps are running on a device right now, these are all sensitive things, so it makes a lot more sense to use them on the device instead of shipping them off the device. I think I'm probably running over time, so really quick recap. Devices are powerful, devices are personal, and devices are here. You know, this is not some science fiction thing. In 10 years' time, we'll have so many devices around us. All of these devices are around us or with us right now. And to make the most of these devices, instead of treating them as just conduits to send in the data to a centralized location where you can run machine learning, we can instead look at a world where we bring the machine learning onto the devices themselves and use the data on devices and use techniques like federated learning to make many devices collaborate with each other without sharing their data with each other or with a central server. And the place where you might consider federated learning are when on-device data is too sensitive, when it's impractical to upload, or when you really want large-scale personalization. All right. Thank you very much for sticking with me through this talk.
Thank you. Any questions for Alex?
Hello, it was a really interesting presentation. I've got a simple question. I was wondering how you do the validation of the federated algorithm without data.
Sorry, I didn't catch the end of it. I can't quite hear.
How do you do the validation of the federated algorithm without the data?
The federated learning process by itself, you know, there is a word learning in it that is a little bit misleading almost. It's really federated workflows. The key thing is to bring any kind of machine learning workflow directly onto the device. So to evaluate whether a model you've learned in a federated setting is any good, you actually bring your evaluation onto the devices as well. You have each device, for example, when it creates its training data, start automatically splitting off its training data into training and evaluation set. You run one workflow to build the models on the training data. You run a different workflow to compute an evaluation metric on the evaluation data, and then combine that evaluation data on the server the same way you would combine the model updates to yield an aggregate update. So it's really taking any part of machine learning workflow and making it run in a federated setting.
Thank you. Another question is, isn't this system of federated learning vulnerable to some kind of attack from the device where the device sends wrong data in order to corrupt the central model? Mm-hmm. And how can we protect against that?
Yeah, it's a really good question. It's one of the areas of research in federated space is dealing with different kinds of attackers. And there are many kinds of attackers. Anything from attackers who want to influence a model to be in their own direction of some kind, to just kind of trolls who would like to see the world burn, to who knows. A couple answers. One is, this actually is not very different from an approach you might see where you have mobile applications that just takes its training data and sends it off to the server. The attack vector is similar in that attackers can send you bad data. So there are the approaches that you might take for verifying the data. On server side, you might take the same approach and run it on device to try to weed out bad data examples or bad attackers. In the on top of that, in this federated learning world, the server has a lot of the sort of practicalities of making it work are all about server logic, about what will the server accept or not accept. And the server cannot look inside an update, but it can certainly do things like try to determine whether a client is legitimate or not, or it might rate throttle the number of updates any client can give to it without looking inside the update. So these are the kinds of approaches you might look at, but it is, honestly, it's an active area of research.
Thank you. So you talked about all the advantages of federated learning, and that's really exciting. What are the current roadblocks that you see that have to be overcome? And also, are there any performance penalties? Like, what are the problems with it today?
The main roadblock is this is a new technology. And on the surface, you know, I might hand wave and say, well, it's just like standard machine learning. It just runs in a federated space, but it looks exactly the same. And oftentimes it does, but essentially we have not yet, we at Google have not, and we don't think anybody else has, yet built up this experience of running it across a great number of all kinds of different use cases. We have focused on specific kinds of use cases, and we've run into occasional roadblocks, mostly around the software engineering side, not the approach side, but there are some things which we still don't know how to handle well. The most obvious one is any kind of model that deals with, that makes assumptions about batch sizes is going to have a little bit of a hard time with an approach like federated learning, which sort of imposes its own batching on top of it. And there are some ways to deal with that, and oftentimes it's not the end of the world if you have to change your batching strategy around a little bit, but that's one example. So I guess to make a short answer is it's still a new thing, so a major roadblock is it hasn't been proven across a large number of use cases yet. As far as speed, you know, it's kind of a mixed bag. It's certainly like if you compare a, you know, in a lab environment, a data center versus a fleet of unreliable devices that can be online, offline at any time, in that world, the data center will win. There's no question about it on speed. In the real world, it turns out that the latency of building all these data pipelines to bring the data into the data center and reprocess them and run them into a machine learning process is actually often, just through implementation, is on an order of days, weeks, sometimes months, depending on how fast your pipeline is. And sometimes this kind of on-device approach is faster by default because it's by default an ongoing process. It never stops. We've certainly seen environments where we've trained high-quality models in a matter of days, where before they took months, not because they needed months of compute time. It's just like that's the ways that the pipelines were built. And you know, you replace that pipeline with a pipeline that moves faster, and the results come in faster.
Let's maybe take one more question, but let's get Jim set up in the meantime, so that we save time. Who was first? Oh, you asked too many questions over the conference.
How would this relate to something where your model might have like localized variations? So I'm thinking of like epidemiology, for example, where you like might have a centralized model, but then actually there needs to be sort of localized differences as well based on sort of localized requirements or whatever. But with the, yeah, because that wouldn't necessarily be localized to one device per se, but it might be like a geographical thing. Does that sort of affect how this would deal with those sorts of situations? Because I could see it being very useful for that because of like the health-related security issues and other things like that.
But let me see if I give it a shot. But I'll definitely be around as well. Like if I'm not getting the question quite right. You don't have to learn a model across the entire population you have that's exactly the same. You know, given the availability of federated learning on devices, you can break up your devices into independent populations and be learning models within each population that are a little different. So that allows you to have models that are, for example, only for people in a particular geographic location, or only for people with a particular marker or flag to their application. I'm not sure if I'm answering your question exactly right or not. All right.
Well, anyway, let's thank Alex again for the great talk.
Thank you for being here.
And it's great pleasure to have Jim on stage again,
Yeah.
Winner of the AI Startup Battle. So looking forward to hearing more details about distributed TensorFlow. Please, everyone, let's welcome Jim on stage again.
Okay. Thanks. So you can hear me, yeah? Good. So I'm going to talk about primarily distributed deep learning, actually. And we'll do distributed TensorFlow and a bit about our platform at the end. So I introduced this diagram yesterday. I find it conceptually a useful way to understand how to build an AI company. You need to handle data at the bottom. Typically, we will have data engineers who work on this kind of level. And if you can manage data, you can build reliable data pipelines to bring data into your organization to collect it, typically in data lakes. You can have a data science team who can then work on that data. So that'll be nice, clean data. Maybe they can use it for training deep learning models. And if you're really lucky, you have a lot of GPUs and a lot of compute, you can do things like distributed deep learning, which currently is, you can see it as being at the top of the pyramid of the AI hierarchy of needs. And people like Google, Facebook, and Baidu do this routinely. And then the type of people who do that, you might think, well, are they data scientists? Would I trust my Python people to do that? Or do I need data engineers? So I just call them data science engineers. Really, they're data scientists. And I kind of see data scientists being able to spread on this pipeline. They're not stuck in the middle forever. And I said I was going to talk about distributed deep learning. Surprisingly, when I come here, I have to explain to people why I think GPUs are important, right? So that kind of surprises me a little bit, because all the advances we've had in the last 5 years has been really deep learning and GPU driven. I'm going to go a bit through about how distribution is important to help us improve the state of the art of deep learning. So we're always interested in building better prediction models, lower generalization errors. And there's 3 points I'll cover. One is how do we get larger data sets? And I'll talk about that first. And then how do we scale compute? In this case, it's GPUs. And how can we use that scalable compute to find better model architectures? So many of you will have seen this diagram before, or some variant of it. I think Andrew Ng popularized it before. Basically, it said that if I have a small amount of labeled data, maybe existing traditional machine learning models can outperform deep neural networks. But as the volume of data quality, good quality training data increases, I can get better prediction performance, lower generalization error from deep neural networks over traditional ML. So what's interesting about this is that Baidu had a paper, and the paper came out just a few weeks ago. I linked earlier on to a blog entry by Adrian Collier who describes the paper. But they basically quantify how much labeled data I need to get an improvement in prediction performance. So this is the graph. You can see it's actually a log-log scale. So it's a straight line on a log-log scale. It's a power law relationship. And basically what it's saying is if I get into this region in the middle, this part here, so now I've enough training data that I'm on in this region. Well, now I know how much more training data I need to get an improvement in my prediction performance. So we can see that a little bit. This is taken from Adrian's blog. But you can see here that as a company, you can say, well, if I collect this much more training data, I can expect this return on my investment. You probably see this implicitly a lot when you hear about the number of hours that Tesla have driven in their cars. Yeah, you'll say, well, we've gone 2 million. And in their head, they have some number. Yeah? They're saying, well, we want to get to 2 million gets us here, and 10 million hours of driving gets us here, and we'd like to get down to the irreducible error region. So as a business, then, you can invest in collecting that data, because this power law relationship that Baidu found in their paper, they found it in many different fields. They found it in image classification, in voice recognition, in machine translation, and in voice synthesis. So across all these different fields, they saw the same improvement in prediction performance based on larger data sets available. Now, you may be smart and say, well, come on, I'm going to do a better model. What happens if I design a better model? I don't need as much data. And that is true, but what it will do is it will shift the axis down. So we see that red line is the better model. So that basically means if I can design a better model, I will get better prediction performance for the same amount of data, but somewhere, that line is going to stop. And then the angle of the slope will still stay the same. It's not going to change, right? So at some point, to get better prediction performance, you're going to have to increase your data set volumes. So that's data as the so that's why I kind of talk about this from a big data perspective. Big data I see as being central to building better predictive models. The next point is compute. What will compute get me? Maybe I can train models faster. Compute is now used at many of these hyperscale AI companies to get us better models. So the founder of reinforcement learning, Rich Sutton, he basically came out recently, I saw in a talk of his, he said, well, methods that scale with compute are the future of AI. This is the guy who did single agent reinforcement learning, right? And he's telling us that, no, you want to go distributed. And what can we say about the current world and methods that scale with compute? Well, the state of the art machine or deep learning models for doing prediction in CFAR10 and ImageNet, they're two image classification data sets. They're very well known. And they're both recently, this is a paper from early March, it was using what we call model architecture search. So what's going to happen is you're going to run lots of experiments in parallel on lots of different GPUs, and each one is going to have a slightly different model architecture. Maybe there'll be an extra layer on one, maybe there'll be a skip connection, maybe we'll change the learning rate. There'll be small variation on all of these. When we run lots of these in parallel, we can then use methods like evolutionary algorithms to pick the best models. And then in the next iteration, we generate new models based on those particular models. And the state of the art was actually using a technique, a genetic algorithms technique, that picked it kicked out actually the oldest models, not just the best. It wasn't just a fitness function picking the best. It was also kicking out older models. So they use a lot of compute to do that. You can see they said 450 GPUs over 7 days. That's quite a lot. TPUs a bit more. And the improvement you got over another model based on reinforcement learning wasn't huge, but it was a bit. Okay. But if you're at the higher end, if you're working in finance and a slightly better predictive model gives you a competitive advantage, then maybe this investment is good for you. And the same goes for self-driving cars and so on. But lots of GPUs and parallel experiments are not just used to find better models, to do model architecture search. We typically do this for hyperparameter optimization. Now, if you're just working with a UI-driven tool and you're doing a simple random forest model, you're still going to have some hyperparameter search. You might do some cross-validation. This is a natural thing you do, but when you come into the deep learning world, people just tend to forget that and go, well, screw that, no validation set, this is too big, I can't do it. Right? But that's not how people work at the hyperscale AI companies. The reason why we don't think about it is because you have maybe 1 or 4 GPUs on your desktop, and you say, well, the time to do that model architecture search will be way too long. The time to try out all of these hyperparameters, that'll take me weeks. I can't spend that time. This is the outer loop of not training, but the outer loop of finding good hyperparameters. So this is plug number 1. So if you have a platform like Hops, or if you're working in a managed cloud service and you have access to lots and lots of GPUs, you will do this because you will get better models out of it. So then the next thing that comes into our pyramid or hierarchy is if you're going to go and use parallel GPUs, you will need a distributed file system underneath all of this. You'll need it for storing the training and test data and sharing that between, if you're doing data parallel training, your evaluation results, your configurations, your hyperparameters. If you're running TensorFlow, you need TensorBoard to aggregate the logs. Distributed file systems are also important for managing larger data sets. So if you want to read in a very large data set from a single machine, you may not have the capacity for that. If you're doing training with TensorFlow, you'll want to do model checkpointing and hyperparameter search and model architecture search I've mentioned already. So the option comes then where you say, okay, I need a distributed file system. What am I going to pick? I'm leaving out the obvious ones like NFS. So scalable distributed file systems are things like HDFS, our own HopsFS, which is HDFS compatible. and you have MapR and Chef and Ceph and GlusterFS. These are quite well known. If you go to the cloud, you'll have object stores like S3, GCS, and Windows have their own file system. I wrote these are slow, right? Because if you're going to take your data set like ImageNet and copy it into S3 and then try and write a simple program to train with it, you're going to be I/O bound. Your GPUs will sit there idle and just wait. Because S3, you're going to set up a HTTP connection. It's going to have to establish that, and then it'll read. And it'll read at quite low bandwidth. So the read bandwidth you get in S3 might be 10, 20 megabytes per second, which is not very much. But it's the latency that will kill you. Just to give you an idea of where we are, this is plug number 2. In our particular file system, HopsFS, we put small files in the database. So for a real-world data set, 9 million images, it's a bigger version of ImageNet with the same hardware. We can outperform HDFS by whatever, 4.5x for reading images. So that's basically so file systems are not all created equally, and do your homework on them. I think what most people associate with distributed deep learning is the training. So you kind of think, I have bought a lot of GPUs, or I have access to a lot of GPUs on Amazon or Google. My training performance should get faster. And you kind of, in your head, you might have an idea of a graph that looks something like this, that it might not be quite linear reduction in training time based on the amount of available compute, but it'll be pretty good. So what the goal of distributed training, of course, is that if you have a large data set and it's taking a long time to train it, it could be up to weeks, that you can get that down to a very small amount of time. And the hyperscale AI companies, they do this naturally, and it doesn't phase them at all. And the time to train ImageNet, if you do it on one GPU, it'll be on the order of 2 weeks. So Google recently presented results where they did it in 22 minutes. The real big one was last year. Facebook actually showed they did it in 1 hour, and they did it on P100 NVIDIA GPUs. And this got a lot of coverage, in the last year, because people kind of suspected, I think, that, hang on, if I was working at Facebook, I wouldn't be sitting here for a week waiting for a model to train. I'd be doing this in an hour. And then kind of they came out and said this, and people said, oh, okay. And this was followed by a lot of other companies started being more open about the kind of GPU infrastructures they have internally. That's kind of what you would expect. The thing is that in practice, and I'm a distributed systems person as well, that in theory it should scale linearly, but in practice it doesn't always. Particularly I think people get burnt mostly when they go straight in and try and run with distributed TensorFlow. So distributed TensorFlow doesn't scale, and it's not, I don't think anybody is really using it in production. And when I talk about distributed training, implicitly everybody now talks about synchronous stochastic gradient descent. So a few years ago, a lot of people were doing the asynchronous variant of this called Hogwild. But there was a very influential paper by Google just a year and a half ago at ICLR where they basically showed for them that we can get better accuracy with distributed synchronous SGD than asynchronous. So there's no real advantage to going with the asynchronous model. So everything I talk about will be distributed synchronous SGD. So this is where I get back to this issue of the dogs around the bowls, right? If you're going to go with the Google distributed TensorFlow model, you'll be using the bottom thing called parameter servers. And what this diagram is basically saying to you is that it won't scale, yeah? And this is what you'll see in practice. In fact, the line will go down, right? So as you add available compute, it'll actually get slower for larger models. So the state of the art, the current state of the art that people are doing to beat the ImageNet results is an algorithm called AllReduce. And I'll just show you what AllReduce is visually. I won't go through the actual algorithm. I think somebody's presented it earlier in the conference. Firstly, we start with the parameter server model. If you look at the blue box, that's our parameter server, and you can have more than one of them. But in principle, what's happening is on every iteration of SGD, you will read in a batch, and the batch will be split up. So each GPU will read in a different set of training examples from that batch. They'll all compute their gradients. They'll send their grade. Oh, we're going on the left one, sorry. On the left one, you can see that we're doing ring reduce first, I remember. So in ring reduce, it's the same thing. Each GPU is reading in different rows from the same batch, and they compute their gradients, but they send them on the ring. They send them to their neighbors, and they receive gradients from their neighbors. And after a full reduction phase, they gather the results from their neighbors, and they'll all can update their model locally. So every GPU will have a full copy of the model. And that's what you have in data parallel synchronous stochastic SGD. So the same is true in the parameter server model. Each GPU has a full copy of the model. They send the gradients to the parameter server. It either sends back diffs to them, but typically a whole new model gets sent back. And if your model is quite big, then, and you have 256 GPUs and your model is 100 megabytes, you can see that even with a high-end InfiniBand network with 112 gigabits per second, it's still going to take a long time to send that data back. So typically you want a very large batch sizes here. And Facebook had a batch size of 8,000 in their experiments there. And they introduced actually a learning rule for how to train with that large batch size. So you can read up in the paper. So the lesson here is that network bandwidth is actually the bottleneck for distributed training. And if you want to actually do distributed training, you should use an algorithm like all reduce. And as I'm Irish, the cliche, you can say the gradients flow better in all reduce, and you have a nice bottleneck on the parameter server there. And that is a Guinness, and I will be having one this evening. Okay, it is Friday. Just to give you an idea of you show me the numbers, show me the money. This is vendor. Well, it's not really vendor. It's actually Uber who presented these results, and they compared all reduce and distributed TensorFlow, the parameter server model, and for Inception and ResNet, they look not too bad, but when you get to a larger model, VGG is a larger model, has more parameters, and that means there's more network bandwidth required. You can see that for 64 GPUs, distributed TensorFlow got slower. It was only 70% of the throughput. But the Horovod, which is their implementation of all reduce, that got a 40x improvement in training, a reduction in training time, 40x. So the lesson here is if you have bigger model, parameter servers don't scale. Network bandwidth will ultimately be your bottleneck. The corollary there is you need the infrastructure for it, right? So no one is doing these type of experiments on the public cloud, right? You would need InfiniBand, dedicated InfiniBand network. Typically, it's all being done on-premise right now. I think Microsoft actually in Azure, they have introduced InfiniBand, so it may move that way in the near term. But right now, the new results are all being generated on-prem. Okay, taking a step away. So, like, what does this mean in code? Show me the money. I'm a Python person. I don't trust all of this stuff. Show me this in context. So what I've been talking about is distributed deep learning, but that doesn't exist in isolation. Everyone knows that a lot of the work you need to do is you need to build up pipelines. And pipelines will take data, they'll ingest it from some place, they're going to transform it, you're going to have to verify, you have to label feature extraction, and we have to do our experimentation and training and testing and verification of the models and before we finally can get to the serving part. And what we can kind of see right now, at least in the TensorFlow world, is that there is a kind of a convergence on typically the ETL stuff will be done in Spark if it's big data. So organizations who have large amounts of data won't be doing their ETL necessarily in TensorFlow. It won't scale. But the TensorFlow is used a lot, either Keras or TensorFlow on top of TensorFlow for experimentation and training. And then serving right now, you don't really have much else if you're training models in TensorFlow than TensorFlow serving itself. So to do this, you'll need to have some infrastructure, either on cloud or on-prem. Typically, Kafka as a message queue would be a normal way of ingesting data. And then you'll need something, resource manager, Mesos, Yarn, Kubernetes, and you'll need a distributed file system. So TensorFlow serving typically will be done on Docker containers in Kubernetes. Now, this is where we get back to our pyramid. Right now, people are kind of divvying up their teams into, we have the data engineering team who do the data extraction and analysis, and then we have a data science team, and then we have an ops team for managing these and monitoring these models as they run in production. And this is kind of scary for smaller organizations. You're kind of going, I can't do all of this. This is too much. So this is not the way we look at it in our company, Logical Clock. So on our platform, Hops, if you have small data, you can do all of the data prep in TensorFlow if you want, and just do TensorFlow serving. And you don't necessarily need to be a data engineer to do that. You can be just a data scientist. I'll show an example later. And we don't see it as being different teams doing different parts of the pipeline. We see it as being one project, one team who are responsible for the entire pipeline the whole way. And if it needs a data scientist and a data engineer, fine, so be it. If it just needs a data scientist or a few data scientists and one data engineer, fine. You find the right team for that particular pipeline. If it's big data you're working with, you're not going to use TensorFlow on its own. You're going to use something like Spark. It could be Scala Spark or it could be PySpark if you want to stay Python the whole way, and that's OK. And our platform has pretty much the same components that I mentioned earlier, like Kafka, the HDFS, Spark, and TensorFlow and Kubernetes. Well, Kubernetes is actually work in progress, I should say. Some of you who are looking at this are going, yeah, this is fine. I'm going to go Kubeflow anyway. Right? And Kubeflow is fine. You can use Kubernetes. The reason why we think our platform has some advantages over going with the Kubernetes model is there's some operational reasons. Firstly, there's no integrated enterprise security framework for Kubernetes. So you will say Istio, but Istio doesn't give you end-to-end with Spark and encryption in transit for everything, and there's no encryption at rest. Stateful services, you'll still need them anyway. You'll still need your distributed file system. You still need to run etcd, Kafka, databases. No one is running these in production on Kubernetes right now. And then from a data scientist perspective, if I want to run on our platform, well, I just need to install Python libraries from the UI. But in Kubernetes, you'll need to write YAML files to change how many GPUs you're going to use. You'll need to maybe write a new Docker file to install a new Python library. And then when you want to run a pipeline, you have to do the whole startup time. It's going to be very slow. So we have this as stateful data in the cluster. So let's have a look at the code for this, just to give you not to scare you off. If you want to do data prep with just TensorFlow, many of you will have heard of the dataset API. It's now in core. And this is just reading some images from an image directory on the first line files. And then you have a function which will take a batch of those files and return them as a dataset. And then you can do the read function, the parser function, which will do your data prep. So anything you need to do to modify your data, you can do that. And then there's some other optimizations in there because you don't want to run this single-threaded, right? And TensorFlow has some support for doing this multi-threaded and buffering data so that you'll get some performance out of it. But remember, this is going to run on a single machine. So what if I have bigger data I don't want to run on a single machine? I have a cluster. Well, most people will use PySpark or Spark in Scala to do this. And a lot of things that you may think are normal, right? You say, well, I'm data science. I don't want the whole data set. Give me just 10% of it. Well, it's lost me. Then you just put in the sample ratio, the amount you want, right? So this is a new API in Spark 2.3, the images API. And you just get a smaller sample of the data. You don't have to do much work. This code is actually more Pythonic than the TensorFlow code. It's easier to read and easier to write. And here we're just resizing some images and cropping them. And the thing is that this thing will scale, right? So this can run on hundreds of machines and go orders of magnitude faster. We have our own way of doing hyperparameter optimization if you have lots of GPUs. So if you want to train your models on tens of GPUs, if you want to, in this case, if you want to do hyperparameter optimization, you'll maybe want to have different learning rates and dropout rates. So here you can see we have 6 different combinations of learning rates and dropout rates. So if I call the bottom function experiment.launch, it will call this model function above and pass in our args_dict. And it will actually start 6 different executors in Spark, and each of them will run the TensorFlow code we put in there. So typically then, what will happen at the end is they'll write the results to HDFS, and then TensorBoard will aggregate it, and you'll see which ones worked best. So which combination of hyperparameters gave you the best prediction performance. I'll do an example of that later on. What it looks like, just to give you a feel for it, is you can see this kind of thing in your TensorBoard, and then you can visually inspect which combinations gave you a lower error rate. Distributed training is interesting. It's what you can do in Horovod is the platform we support. We also support TensorFlow and Spark, but that's the parameter server model. Horovod requires very little changes to your code in TensorFlow. You basically need to wrap your optimizer in this HVD distributed optimizer, In our case, if we want to launch the job, we do it from a separate notebook, and that's because Horovod runs with MPI run, which we kind of run underneath Yarn. But it doesn't make it too difficult. So if you want to just put normal TensorFlow code, you have a chief in Horovod, which will typically do model checkpointing and so on. But then the rest of the code will just be dumped in those if and else statements. The API is bigger than this. We have our own API for managing TensorBoard using HDFS. And we have another one for model architecture search with genetic algorithms. And there's other ways of making it easier to read and write from Kafka and so on. If you want to do model serving, then we have a REST API, but you can also use the UI just to pick your model, press serve, and then you'll get at the endpoint of the model, and you can use gRPC to then make calls directly on the TensorFlow model server. Okay, we're out of time. Okay, so I'll just this I kind of covered the last time, so we'll skip through it, and I have 25 minutes here, but okay, we're good. So I went through this the last day, so I'll skip over that. Yeah, you can do Python per project. This is all integrated in the platform. I have a video. You can, if you want to have a demo of this, you just talk to me, I can go through it with you. It's online. And yeah, just to summarize, a quote from Andrej Karpathy, this is basically the way things are going. Deep learning workflows will be distributed, they will be auto-tuned, and even the schedules at which they run will be auto-tuned. So that's it, and that's our team.
Thank you very much, Jim.
Okay.
Any questions for Jim? Oh, yeah, right.
Another Irishman here. So thanks for the talk, but what do you feel in terms of like specialist APIs for like machine learning, like, you know, in general? Like, so you've done all this kind of work with your company. Do you see this as like an inevitable thing that will, like, you know, companies like Facebook and stuff will build themselves, or like, you know, how do you feel in terms of like, you know, the gap between what people are saying, oh, TensorFlow can do this, and all the other work you have to do on top of that?
Yeah, it's a tough question. I mean, we know what the hyperscale AI companies are doing right now, and they're doing extremely impressive things. I think it's more a question of what can other people do to catch up, you know? Yeah, and you know, you can go on cloud and you can pay for Google's managed TensorFlow service, and it's quite good. If you're stuck on-prem, you can talk to us. But ultimately, I think, you know, just my feeling here is that people haven't even got up to GPUs yet. And you really need to start, if you're going to be doing deep learning, you need to be working with GPUs primarily. And once you start doing that, then you'll see naturally that, hey, if I have 10 GPUs, I can you know, do my experimentation 8 times faster. And you'll just work that way. I mean, the question about what APIs and so on, we think TensorFlow is one of the dominant platforms, so we support that primarily. Keras will be very big. It is already. The rest of them need to catch up, you know.
Let's maybe take one more question, but again, I'm going to invite our next speaker to come up on stage, get set up while we're getting the last question, if there's any last question. All right, great. Well, let's thank Jim again for his nice talk.
Thanks so much. Fantastic. Yeah.
All right, our next speaker is Darko, who's the CEO of Causalence. And Darko will speak about automated feature generation. I guess that was a topic also earlier today. I missed that talk, but now I think the focus is going to be on time series prediction, so potentially a little bit different from what was presented this morning. So please join me in welcoming Darko on stage.
Good afternoon, everyone. I'll keep this short and sweet. I know you're all tired from a few days of talk, so I'll keep the I'll keep the talk straight to the point. So just to give you a background of what we're going to talk about, we're going to talk about how do you solve real-world time series prediction problems. So this is very much in the spirit of the conference. So with this approach, you can actually go and make money on the market. So it will be worthwhile, listening to. So what we do is automated machine learning. So we believe that general artificial intelligence, it's not going to exist in the short to medium term. So in response to this, we're building kind of almost like a narrow AI, realization which solves one particular problem very well, and that problem is prediction, automated prediction algorithms for time series data. So the title of the talk is long, but you'll see what I mean by all parts of that throughout. So just to motivate the talk a little bit, first to talk about where you can find time series data first. So time series data, the obvious place is finance. There's a lot of it there. To think of it as a stock price, macroeconomic variable, anything. You can think of every server in a server room will produce time series data. Autonomous vehicles produce time series data. If you're Uber or the likes, you have tons of time series data that you can help you predict demand for your services, or how many people are going to call Uber in the next hour. If you're a commodity trader, you might want to predict temperatures across regions, which drives electricity generation. Health data is time series. It's there's a lot of time series data around if you know where you're looking. With the IoT, we will have 50 billion connected devices by 2020. So one report said. So point is, time series data is exponentially growing. So knowledge starts with a definition. So let's first define what we mean by challenging time series problem. That might not look like a challenging problem in context of what we heard about, deep learning and scaling deep learning across multiple servers. But actually, this is super difficult problem to solve, and it's actually very difficult because it's a small data problem. So if you, for example, were predicting, how many cars are going to be manufactured in China, or you're predicting price of Apple. There is some limit to how frequent the data is. So the data that is over there, for example, is at monthly intervals. And you might have a bunch of drivers that are related to this variable. Those drivers might have a very low signal-to-noise ratio. And you might have a lot of them that have a little bit of signal, each of them. So most importantly, the reason this is very difficult is it's what is called a non-stationary time series. And a non-stationary time series, it means essentially, a complex definition, but in summary, it means that the mean and variance of this thing do not remain constant over time. So the mean and variance change. So this makes it a particularly difficult problem for machine learning. So if you just plug this into a machine learning classifier, you're not going to get very good results. Anyway, so the focus of the talk is how do you solve this complex real-world time series problem? How do you take the stuff on the left, fit it into some box that gives you, accurately predicts the thing on the right? So the answer is actually you need to do a lot of things to get there. We all love deep learning. I love it too, but on 200 data points, it's not going to work very well. Econometricians have been doing this, since the 50s. Unfortunately, the techniques are pretty simple, so again, it's not going to work. It's, if you like, those are the two kind of ends of the spectrum. We have econometrics, kind of very simple, ARIMA models, all the way to deep learning. So to solve that problem that I show you, you need to be somewhere in the middle. By the way, as a company, we do the full spectrum. So the focus of this talk is just on this particular use case, but in general, we cover the whole spectrum. So to solve this problem, you need to actually use human intelligence, which is not something people talk about on these kind of conferences, but actually it's vital in solving that complex problem we define. Then you need the boring stuff of how do you optimally impute and align the data. And actually it might seem trivial and you might kind of pass through it, but it is super important. And I can see someone nodding there that is doing this on a daily basis. It's really absolutely vital how you do it. And then, feature extraction. We heard a lot about this. I don't need to repeat myself. All I will say is feature extraction in the context of time series is unique. So special care has to be taken, not to introduce forward-looking biases and all that sort of stuff. Feature set selection, again, everyone in this room knows, why that is important. And, in summary, it's because of curse of dimensionality. More data, more inputs in a low signal-to-noise ratio does not mean better performance. Then we have the notion of, which algorithm do you actually choose? Is it going to be random forest? Is it going to be gradient boosting? Or, what algorithm is going to deliver on this? And then how do you tune the parameters of that algorithm? So that's, if you like, the full pipeline you need to solve in order to solve that challenging time series problem. So I'm just going to show you kind of some experiments we did this morning on the Causal Lens platform to demonstrate the value of doing all of these steps right. And then we're going to introduce some cool ideas of how do you put all this together in order to solve this full problem, and you can make some money with it if you get it right. So here it is. First, let me explain you the experiments we did. So we wanted to prove out the value of doing some of those steps in a constrained environment. So we wanted to introduce only one covariate at a time. So like a proper experiment, proper scientific experiment. So the idea is we keep the algorithm part kind of to the right of the algorithm selection constant, but what we change is the feature selection and the feature extraction process. And we want to see what is the impact of actually doing that properly. So we've run this experiment across a number of data sets, and we measured them across a number of metrics. So what I will show you in the next slide is distributions of those results. So here they are. So first, the value of humans. For these complex problems, and I'm sure if you speak to practitioners in finance, there's a kind of a divide between the guys that believe the machines and the guys that only believe the humans. And we've kind of been showing to the world that really it's about the middle. And this experiment clearly shows that. On the left you have the mean absolute error. On the right you have the Pearson's R between the ground truth and prediction of the experiments. And then on the bottom you have the number of data sets on which we ran this. So what you can see clearly is that introducing a human element into selecting what goes into a model can improve performance by a lot. Yeah, and that's across a large number of different types of data sets. So I didn't want to include and bore you with the statistical tests and all the parameters. I just put one line saying it's statistically significant. But we did t-tests and all sorts of stuff to prove it that those distributions are statistically different. So humans, important on these small data problems. Two, feature extraction. So there's the experiments are using simple feature extraction and using more complex feature extraction. In the time series world, this means, do we just extract one difference and we add the value of the time series, or do we extract more complex features? Do we try to learn, momentum? Do we try to learn mean reversion? Do we take multiple step differences? All these complexities that exist in, for example, financial markets or any actually physical system. So what you'll see that it does pay off actually to extract this time, if you like, from time series. Feeding directly the values of time series will give you the distributions in blue. But if you extract the time element from time series, you get some impressive results. And this is proven across large number of data sets, across large number of model algorithms, and across large number of parameters. So far, human matters, feature extraction matters, especially for time series, because without that, you do not have time from the time series. Second, restricting what goes into an algorithm matters a lot again. And this is especially the case for these small data problems. So what you'll see again that, if we have a clever way of selecting features and then feed them into the models, the evidence is there that across large number of models, across large number of data sets, it makes sense to do that. So if you remember, the first slide was about doing a bunch of things in the pipeline, and then we come to which algorithms we select, and then which parameters of each algorithm. What you will find actually, if you try to optimize across this whole space, it's actually a multi-dimensional discontinuous space. So people call it derivative-free optimization or black box optimization, whatever you want to call it. It's a hard problem to solve in general, but we have done some really cool tricks to solve this problem for the time series world. So we have essentially trained and optimized it to learn how to solve time series problems. So how do you traverse this discontinuous space in which you cannot find gradients in an effective way? And I don't want to bore you. It's Friday afternoon. But we can chat about how you do that. The idea is that doing it properly, it helps a lot. That's your evidence there. So in the first experiment, it was doing everything kind of isolated, one at a time. When you put it together into this full pipeline and then optimizing across this space, also helps the models. So now I want to show you, how I did all these experiments. I ran maybe 6 months of human experimentation time in 15 minutes this morning, and the reason for that is because we have this cool machine which can do this kind of experiment. So you could, given that's. So this is kind of the data you saw in the presentation, and all I was doing this morning was running cool experiments by clicking this button through the API. And what this was doing you cannot see it. It's a bit strange. Okay. What this button did is essentially ran through all of those steps in the pipeline and optimized it, and then it gave me back kind of the most promising full models. So notice I'm not saying algorithms, I'm saying full models. A full model includes how do you extract features, how do you select features, which algorithm do you select, which parameters do you select, all that stuff. So I just want to show you kind of the winning model from that little discovery process, and you can see essentially that only with kind of 200 data points of this data, we were able to learn a model that solves this very complex time series problem, which is non-stationary, small data, all that stuff. Cool. So I'm just going to leave you now with. If I can find my mouse, with one kind of idea that I think it's kind of the future of machine learning in general, is this notion of that real data is dirty, hard to find, and it doesn't let you really push the limits of what's possible with machine learning. So the way we solve that very complex optimization space that is discontinuous and you cannot find gradients is by generating a lot of artificial data. So very, very much like the breakthrough Google had with AlphaGo, is generating data with known properties, adding some noise to it, and teaching your optimizer to learn on a specific problem. In our case, that is time series predictions. So I think, in general, we think that there needs to be more move towards doing this in order to solve, very hard problems in an efficient manner, and the things that work in the real world. So on that note, I will just introduce us. In general, we are early stage startup based in London, and we do one thing, and we do one thing very well, that is time series predictions. And we have attracted some of the world's largest financial institutions as customers because they're very passionate about efficiently solving real-world problems with noisy data in situations where they have only a small number of data sets available. But that's my co-founder there, Max. He can tell you even more about all the fun stuff we've done with optimization. So thank you very much. You can have beer now.
Well, coffee and tea first.
Yeah,
beer would be afterwards.
Sorry, yeah.
And after the coffee and tea, there'd be a panel discussion.
All right. Sorry. I was predicting the future wrongly.
No, it's going to happen at some point, but timescale was different. Any questions for Darko? You guys really need tea and coffee?
Yeah, I think so.
In the demonstration you showed there, where did the human element come in? What do you do?
Right.
You said you pressed the button and it took 15 minutes, but what was the human?
Right. So imagine you're predicting price of Apple. So you could say, hey, I'm going to give the machine everything from all the financial market data. I'm going to take Bloomberg and I'm going to give it to the machine. So that is essentially suboptimal. What the human element was, in this case me, was to say, hey, for this particular prediction problem, I think I have maybe 100 candidates. So rather than having 10 million potential inputs to the model, I restricted the set by knowing what things could potentially have an economic significance in this particular case. If you were doing a problem that is related to demand prediction, for example, you might want to, you're not going to include every single product in the world. You'll say, well, let me think first about what could potentially impact the demand for this product, and I'm going to restrict the space, with using some human intelligence.
A question on your business model.
Yeah.
Is the plan sort of that you're able to generate a higher ROI through providing this as a solution for others rather than using the insights to trade yourself?
Yeah, this is probably the most commonly asked question, and I think there are business models both sides. If you look at the background, we come from some of the world's most famous hedge funds, so we know how to trade. We've been trading for quite some time. I guess it's a strategic question. What is bigger? If we set up a hedge fund, we might attract 10 billion. If we sell this to every company on the planet, the opportunity is bigger. So that's as simple as that, really.
No more questions? 3, 2, 1. Oh, no.
Is the automated part all about the feature selection, or is it the models as well? What gives you the edge?
Yeah, I get. So that gives me feedback that I need to improve my delivery of talk. But yes, it's essentially about the full pipeline. It's about doing everything. Starting from dirty data to an optimal model in a single API call. And I actually didn't show you that bit. That's how you would really use this. Our product is extremely simple. It has one API call for discovery of models and one API call for running models in production. So when you throw this one API call, what it will do all parts of the pipeline, including backtesting and scoring models, and it will give back the best model possible for your problem. And then you can, essentially productize that and have one line of API, one line of code that can run this in production.
How does it? What evaluation metrics is it using? Because you'd want different evaluation metrics
Right.
for different time
Of
series and
course.
different objectives.
That's right. So it's using a plethora of metrics, maybe 20 or 30 at the moment, but you have control over, what is a good model for you. So we typically tend to see people, creating, we call it the causal and score, which you can actually tune and say, for me, a good model is one that performs, across all these metrics with a given, function of your choice. So you can pass a function, which is function of all the possible metrics that we compute, and it's your function, so it will optimize according to that.
Thank you. Follow-up to that question. So do you guys actually provide a predefined way for every step of the pipeline? Or do your customers have some input on the human element of it? And then second part of the question would be, what do you actually use for your optimizers? Thank you.
Right. So we think that what our customers really care about is getting the best possible model. They don't really care how you got there, which is why if you're a portfolio manager, you really just care about predicting what your macroeconomic indicator is going to be. You might not even have any notion of data science at all. You really just want to solve the problem, and that's kind of what the product does. And the second part of the question was?
What do you use for your optimizers?
All right, so we use genetic algorithms, for example, that when you're in a discontinuous space, you have to do that. But there is how we train them. It's kind of where the innovation. So we train them specifically on time series prediction problem with generated data.
Okay, let's thank Darko again for his great talk. And quick shout out before going to get coffee and tea, and I think there's still a little bit of food if you're hungry. So CAP AI is our video sponsor. In case you missed some of the talks in this room, you'll be able to find them on our YouTube channel. Just search for PAPIs.io. And CAP AI is interesting in connecting with talent, academic talent in AI and machine learning for placements in interesting startups, exciting startups. You've seen that there's quite a few opportunities to work on very exciting things through the AI Startup Battle, but also some of the startups that have presented today also at the conference. So if you're interested in that, feel free to approach the people at CAP AI and Capital Enterprise. And is Lizzie around? Maybe not. Well, you'll be looking for Lizzie. She knows everything about that. Otherwise, if you can't find Lizzie, maybe John can point you to her. Yeah. All right. Thank you very much, and see you after the coffee break for the panel discussion back here.
Right, so we're going to get going. It's the last thing of the day. I didn't really intend it to be this way, but somehow I've spoken first and last over the course of the 2 days. We're going to have a quick discussion about some of the things we've seen over the course of the 2 days and where we think things might go in the near future. And to do that, I'd like to invite two panelists, Libby and Noor, back to the stage. I think they've both spoken at certain points during the last couple of days. So maybe, given that some people have only come for day 2, etc., let's just recap, say, in Cilla Black style, you know, what's your name and where do you come from?
Hi, I'm Libby Kinsey from Project Juno. Where did I come from? I spent just over a decade investing in physical science and computer science startups here in the UK. And about 5 or 6 years ago decided I wanted to do machine learning. So I went back to UCL, in fact, to do the machine learning masters. And for about 2 days after graduating from that, I felt superpowered. And then I realized that I had no idea to actually turn machine learning into valuable products and services. I didn't have any of the DevOps or infrastructure skill sets at all. And it seemed like a lot of the companies that I was talking to join didn't know those things either. So this conference is kind of really at the center of the sorts of things that I'm interested in. How do you turn machine learning into valuable products and services? And what's the environment like? What are the societal impacts that might impact how you try to do that?
Thank you.
I'm Noor Shakir. I'm originally Syrian. I did a bachelor in computer science engineering back in Syria and then moved to Belgium, Leuven, did a master in AI. And from there I started my academic career. I moved to Copenhagen in Denmark. I spent about 8-9 years doing PhD, postdoc, started my assistant professorship at Aalborg University in Copenhagen. I was mainly doing AI, machine learning for generative models, GANs and deep learning models weren't really popular at the time. So I was doing mainly genetic algorithms, neural networks, and combination of both. I was mainly interested in a field called procedural content generation, which basically means GANs, or like generative models, but the old style. I was doing that for games. And I was particularly interested in understanding user behavior and coming up with content or with like particular pieces of new games, new levels that meet that behavior automatically. So like kind of closing they call the effective looping game, basically sensing emotions, feeding that into model that can come up with new content and then let the player play, and kind of like this kind of loop. So I spent quite a lot of time doing that kind of research, and then as I entered the professorship world, I kind of looked into the future of like my career path, and I thought there's still like a lot of things that I can do that I enjoy really doing, and I can do it a bit faster and be more productive if I am not in research. So I decided to leave academia. I moved to London, March last year, joined Entrepreneur First, and started my entrepreneurial path. I met my co-founder, who has a physics background, and we started GTN. And I've been working on GTN for the past 9 months as a chief exec.
Maybe just say a very short what the company does.
Yeah. So GTN stands for Generative Tensorial Networks, and the idea is that by building like interdisciplinary innovation, we can provide really, really good insights and way more efficient way of doing drug discovery. And by that I mean like opening up a new space of chemicals that are unseen or unreachable before. So going beyond what humans have seen throughout the humanities and opening up a totally new space of chemicals that could become drug, making the whole process of drug, kind of like disrupting the whole process of drug discovery by just opening up new possibilities.
Very good. I think what the format is, we'll sort of set this up for 10 minutes or so, and then we'll open it up for questions from the audience. So get thinking. We'll be asking for a show of hands in short order. If we think a little bit about what we've seen, you brought up the point about the kind of DevOps and actually how to roll some of this out in practice. Where do you think we are in that adoption curve for companies? So we will have seen over the course of the 2 days a variety of different applications. Everything from graphics through to time series in finance and things like that. Where do you think we are on that adoption curve for every company having some sort of machine learning enabled product?
That's a mean question. Actually, surprisingly few AI enabled products and services at the moment actually use machine learning, and even fewer deep learning. So there was a McKinsey report last year which surveyed lots and lots of corporates and asked them whether they were deploying anything or whether they were thinking about it, and it was a small percentage, although I can't remember exactly what it was. And I think that's partly because we are relatively early in the adoption cycle, particularly of deep learning, and those that have deployed in the real world tend to be the GAFAs of the world, the social or search huge corporates, Google, Amazon, Facebook, and Apple, who have access to very, very large amounts of data and large data centers in which to process it. And that's kind of has been beyond the expertise and money of resource of lots of not even very small companies, sort of small to medium ones as well.
If I think about the work you're doing in terms of Juno and the mapping, which sectors do you see a proliferation of potential applications? Is there a leading sector?
Well, part of the reason we did that is that we had seen a lot of noise made about ad tech, things like that. So the early adopters tended to be in those kind of spaces where e-commerce, for instance, where you might have a lot of data, and that kind of seemed a bit dull in terms of what you wanted to get up in the morning and do. So we wanted to me, maybe not to everybody. So we wanted to shine a light on some of the other applications, and actually they are myriad. And there's lots happening in all kinds of different spaces, but there are some where adoption has taken longer, and perhaps manufacturing or the creative industries might fall into those categories, and that's probably again because of lack of data.
When you were joining EF, making a transition from gaming into drug discovery, talk me through the process of identifying that as a particular sort of target sector that you wanted to get into.
Okay, so I don't really have like structure way of like how things went until we kind of tapped into drug discovery, but kind of like it's kind of like fun story. Just met my co-founder, and we felt like together with like machine learning and quantum physics, we can do something really, really cool. And
it's got a lot of good words.
Yeah, it's like yeah. Okay, I'll go with that.
Just say blockchain as well. And then we're there. We're done.
No, I'm not gonna do that. So I feel like drug discovery is way more exciting, by the way. So yeah. Well. So we started like looking into different verticals, and there are a number of them that sound really exciting and like has a lot of potential, but it just like we didn't really feel that the kind of the impact would be really great, and like this, in terms of like a social impact, the benefit, and like kind of signifying the use of the technology, until we kind of looked into drug discovery, and the inefficiencies were really like. It was like the whole thing was really shocking. The kind of like how it is right now, the expectation into the future, and kind of like, and the fact that all of these inefficiencies, and then by the end of the day, it's like people's life. It's really huge, and what we had was kind of like the best fit to the field. So kind of like just decided to go after it.
In that sector where you do have very large, well-financed companies that are in principle used to using data, why do you think, as you see it at the moment, they're behind the curve?
They're way
in
behind.
Adoption?
Yeah, they're way behind. I think the main reason for them to be behind is they're kind of not really a risk takers. So pharma has like lots of money, lots of data, but they tend to minimize the risk, or like the financial basically risk, because the whole process is already very, very risky, with like 90% or more failing, of the compounds failing later in the clinical process. And you want to minimize that, and taking more risk by trying something really novel, really new is like, will add to it. So they recently, like for the past probably 5-10 years, they started to kind of outsource a lot of the process. So they can put lots of money in different places and then try like to get people to do whatever they want to do with innovation, and then take the one that succeed. Which is, yeah, I mean, they still fall behind, but at least they will get to kind of influence other people as well. And you get access to the data, you get access to resources as well, which is
very good.
Yeah.
Depending on where we go, I might go back down the rabbit hole of sort of empirical testing, drug discovery. Yeah. But let's leave that for a second. It's not necessarily a medical audience. Just before we open it up, maybe for a couple of questions, Libby, you've written a couple of blog posts that I have read about the AI winter. Right, we're going through several different waves of machine learning and AI technologies, and we seem to make accelerated progress over a certain period of time, and then we slow down and the adoption doesn't quite happen and the use cases don't quite materialize. Maybe you just say a little bit about how you see that happening. One, explain it for the audience that haven't read the blog, and then maybe we could talk about this third AI winter and whether it'll happen or not.
Yeah, sure. So I was thinking about what might cause the current wave of confidence in machine learning products and services to have some kind of check, less investment. And the way that came about is I went to NIPS in 2016 and I was talking to a lot of people there, and it seemed that some things were happening which on their own might not presage a kind of a bubble, but together seem to suggest that we're in at least something that's a little bit frothy. So, for instance, the kind of investors that wouldn't normally take technology risk are coming into this space. So the Goldman Sachs of the world and sovereign wealth funds, that's kind of sometimes a little bit indicative of something a bit bubbly. And the kind of salaries now that startups are having to pay for talent. I mean, there's just such a lot of competition for talent in the space. So what does that mean? That kind of means that innovation is getting more expensive, and investors, if it is a venture-backed startup, may not get the returns that they need. So another kind of anecdotal piece of information from that conference was that some of the large corporates that had been very active in acquiring were having real trouble actually deriving value from the startups that they'd acquired. And the other side of things was around the societal implications and the perception of AI. And I guess it's perhaps there that things have moved on even in the last year, the sense that there are becoming haves and have-nots that are being entrenched because of access to machine learning technologies, and that biases may become entrenched if we don't take some of the ethics seriously. And the fear of job losses. So I'm not even talking about fear of singularity. These are much, much more kind of concrete fears, and I think they are justified. So there's a lot still to do to make sure that we develop machine learning products and services that the public continues to think, on balance, are good for them, and that we can continue to build at a cost which makes it worth investing. If we don't do those two things, then I think there could be a winter. But I'm not saying there's going to be. I'm a massive optimist.
All right, we'll take questions in a couple of minutes. Maybe, Nora, just before we sort of throw things open to the floor, comment a little bit about whether you see some of the technologies you've been working in that industry displacing jobs. You've talked about inefficiencies in drug discovery pipeline. I know I don't know enough about the industry to understand what the consequences or knock-on effect of automating various parts of that would be. Where do you think this will go?
So I think AI is kind of like, what do you call it, like two-faced sword or something? How do you call it? Like a sword with like two double-edged sword. That's it. Okay.
Thank you.
Thank you. So it's basically, I mean, for us at least, so the way we see it is that we are improving the efficiencies of drug discovery, which basically means that in some way we are taking some of the job that chemists would usually do and automate it, which basically means that we're like, some of the chemists will lose their job. But if you look at the other side, what does that mean is because we're increasing the efficiencies of the whole process, we are also reducing the amount of money you have to spend on drug discovery. And what that means that probably in like 10 to 15 years time, it's not going to be limited to only pharmaceutical companies to be able to fund the whole process. They're going to be like more medium-sized startups, medium-sized companies being able, because the kind of the whole process is reduced, the amount of money you have to spend is reduced, will be able to afford the whole thing. So it's kind of like taking jobs from some areas, but opening up other opportunities in other areas. So you need to look at the whole picture in one way or another. And the other thing that I really like to think about AI in a positive way, and I really like the idea that humans are really creative individuals. So if you give them like a bit of freedom in time, they will figure something out and they will use it wisely in a way. It's just like building this culture around you. I mean, it's okay to work less amount of hours per day and just be creative in the rest of your day.
Yeah, so we're all going to have long holidays. Sounds good.
Which is great, yeah.
Yeah, I guess if you look back through human history, obviously for the majority of it, we didn't clock on and clock off on a 9 to 5. So, any questions from the audience in terms of things we've seen, transitions, trends in the space? Otherwise, you'll just have to listen to me talk, which I'm okay with. But yes, we got a floor mic anywhere? I'll roam. Look at that. Don't say I don't work for my supper.
One thing that was very apparent in this conference is how many actually very good presentations have been done by the likes of Google and Amazon, etc., and how they're trying to position themselves to be enablers. But there's obviously a bit of a tension there, double-edged sword again, between how much of the space is going to be us servicing the GAFAs and how much where is the opportunity for new startups and others to actually take them on. So what's your view on the relationship between startups, developers, and basically the GAFAs?
So my take on this is like, so these big giant companies tend to do things that are kind of like, they tend to care a lot about how big the market is and like how big the market and the product and these kind of things. The nice thing about startups and why I think most of them work and have like potential is because we tend to like be really, really focused on like solving specific problems and solving it in a way that is like really innovative and really, really fast, which is something that you can't really do in big corporate because of like the hierarchy of decision making, because of like how they work in general, because of like the difficulty in collaboration. So if you're building like something similar to what we're building with GTN, like bringing people from like chemistry or physics and machine learning together and putting them to work together, it's really, really challenging. And I feel it does work because we're still small, we're still agile, and we can like really move quickly, figure out the problems and try to solve them very quickly. I can't really imagine such an interdisciplinary setting would work really well, either in big pharma or in Google or in Amazon or somewhere else.
Yeah, I'd agree with that. The whole thing that Forward Partners was talking about yesterday about looking at verticals where you need domain experience, and that might come from having access to proprietary data that those organisations wouldn't have in that vertical, or it's becoming increasingly important to think about knowledge representation and non-data approaches to intelligence. So the kind of expertise that you need to build those priors into your models. Those are probably areas where the large corporates don't have any interest or skills to go into. And then it's a positive that they're putting all of this amazing infrastructure and expertise out there for use by everyone. I think the only reason they can do that is that machine learning is being done in an unprecedentedly open way. All of the algorithms are available, the model zoos, the research is happening in a very open way, and it's being done that way because the value is in the data. So Baidu and Google release their research because they hold the data for their application areas. But if you can find other application areas, then you've got all of these great resources to use.
Another question? Yeah. Just anecdotally, on John's point, I think AlphaGo costs £10 million in electricity for training, right? So there's a definite things that a startup can do and things that, they can't.
I was just wondering if you could comment on, as you said, these big firms have an advantage in the data that they've gathered over so many years, but we're now seeing customers are able to go to these firms and pull all of their data. So if millions and millions of customers pulled all of their data and somebody else come along and said, give me your data, you could recreate a Google search engine, a Facebook, a Maps, pretty much anything that you wanted. Do you see that potentially happening?
I wonder how that would happen in the real world. So Azim Azar's got a really nice phrase for this, which I forget, but the dominance of companies like Google is only growing, in fact, because the products and services they provide are so sticky, people are using them more, and then they're collecting more data, and they can provide better products and services. So I guess a kind of virtuous circle. He would say it in a much more fluent way. And I kind of can see theoretically what you're saying, but I just can't imagine it working in practice. On the other hand, I do see that innovations in how one takes control of one's data and potentially gets some reward for sharing it with products and services that they want to use. I think that's a really interesting sort of area of opportunity, and starting to see lots of startups thinking about that. I think there'll be a combination of regulation and these kind of business model innovations that will give us back some control of our data. I hope so, anyway.
Any further
That
comments?
was another really difficult question.
Yeah, we've had a couple of sessions on GDPR-related activity. I think the too long didn't read version of that is, I think we have to wait and see how it's interpreted by the courts. Right to forget is unlikely to generate the instant exodus of vast amounts of data from companies, but we shall see. Anyone else? Someone at the back? Maybe I'll ask again another slightly unfair question. If we've gone through waves of different algorithms, for the sake of argument, and we're in the current one where the recent successes of revisiting neural networks with vast computational power compared to what was around when they were originally invented. Again, another sort of anecdotal piece of information. I think the architecture for AlexNet, like one of the big first networks, if you were doing it in kind of 93 or 92 when it first came around, I think they calculated it would take 250,000 years to train. So one thing we've definitely seen in terms of the availability of compute is like certain types of experiments and therefore progress on certain types of machines just wasn't really possible over the last couple of decades. And now, not just from the individual architectures or machines themselves, but the difficulty of running an experiment that takes a long period of time, and the difficulty of holding together research teams over a few years in terms of dedicated groups of people. And suddenly we've got to the point where actually you can start to make a reasonable amount of progress on quite large architectures. I wondered whether, given that's the wave of success we're currently in, whether you things like, pardon me, symbolic reasoning and other sorts of things which are now untrendy and where we seem to be making less progress, things like grammars, things like the structure of priors, whether you think we will get to the point where this current wave has sort of run out of ideas and we have to revisit some of these other areas of computer science in more detail.
Well, we already are. I think this is really fertile area. And so, for instance, you may have seen DeepMind hired Murray Shanahan from Imperial and hit a couple of his research students with a paper which was combining deep learning and symbolic reasoning. And they've been doing quite a lot of work in that, so trying to incorporate structure from the symbolic and relational side to end-to-end deep learning approaches. And there has been a little bit of a debate recently. I don't know if any of you follow Gary Marcus on Twitter or have seen some of the debates at NIPS, where he's been arguing that we need knowledge representations and structure and models to play a much bigger part in getting from perceptual reasoning to some of the higher level kind of intelligence, where you might want to well, I suppose reasoning being one of them. I've lost my thought process. What are higher level cognitive things you might want to do? Yeah, that aren't perceptual.
I would think like there's like two, like in my mind, there's probably two directions to answer the question. One of them is deep learning has been really cool and really like efficient and solve some of the really great problems in terms of classification, understanding text, prediction or generation of images and text, but they're quite limited in a sense of like what kind of problem they can solve, how much data they need, and the expressiveness, so you can't really understand what's going on within the black box still. So like we're using a lot of deep learning at GTN, but explaining the outcome to a chemist, or like why this drug structure is way more interesting or way more effective than the one you've been working with. How do we explain that? How do we explain how the method came up with that solution is something that we would be interested in at some point, and I don't really have the answer about like how do we go about it yet. And the other thing is that there's like specific types of problems where deep learning hasn't really managed to do anything really interesting, and those are the problems where you either don't have enough data to train the models, or the problem is really, really complicated and like multi-model kind of, that you can't really do deep learning on it. My favorite example is emotion, human emotion. Like how do we understand human emotion or cognitive affective states? And so far it's been like just about reading faces and understanding who is that. But where do we get to the point where we're actually building emotional intelligence, where we can actually respond in a human way? This is something that I haven't really seen a lot of progress in, and I don't really think deep learning will be the solution.
I don't know whether I agree with that.
Here we go.
I think emotion is one of those areas which is so difficult to have a formal definition around.
I agree. I've worked a lot on that, and I work specifically on like building neural network to mathematically capture like engagement or fun, frustration, challenge when players play a game, which is something you could imagine it won't work, but it worked up to a certain degree. So you can like predict actually how engaged a human is when playing Super Mario Bros, like 70% or like 80% accuracy. It might not be that really that accurate, but it is good enough. And I feel like there's a lot to be done within that area. It's just that it is so hard to like capture all the dimensionality of emotion, all the modalities that you can feed in the model.
Yeah.
So there's like not really a clear way about how do you go about it.
Yeah.
I want to give an opportunity for an easier question.
Yay!
So could I ask both of you about a new application in machine learning that you're particularly excited about, or that you'd like to see move on more?
Oh, that's a hard one.
Oh, I'm sorry. Yeah. I thought it was fun.
Tried.
Do you want to go first? No. I think some of the more interesting things are, is shibboleth the right word? Things that we sort of, ideas we hold dear. The idea that creativity perhaps is a really human domain. And I think that some of the machine learning innovations have started to make people feel a little bit uncomfortable there. So I'm interested to see where they go. And I think there are definitely business models which can walk a path which humans will be comfortable with as well. I've given you time to think.
Yeah, I know. It's like good. So one of the, I mean, I tapped into like drug discovery very recently, and I really love like the area. And the more I like think about it, and the more I read about it, it's like you can see how many problems are in there, in like not specifically in drug discovery, but also in understanding human body and how it works, and how do we get from like a disease up to a point where we can actually cure the disease with like all the computational. Like, just imagine like that we have a way to kind of have a chemical and put it in a computationally created body and figure out all the complicated processes that goes in there and be able to predict very accurately whether it's going to be an effective drug or not. We are like very, very far away from that. There are like some models like for like the kidney or the liver, computational model to simulate those, but it's still far from actually having a fully comprehend model of the body and how it works. There's like the genome sequence project, which is like also something really exciting, and I feel like it's just that there are lots and lots and lots of problems within this field, and I feel like there are also lots of solutions. It's just that I'd really like to see people within different disciplines talking more to each other and figuring out problems.
Well, given this is sort of associated with the School of Management, and we've had talks from infinite loops of giraffes through to distributed architectures, I think that's a good place to end it. This is intended to be a conference that has a very broad audience base and explores a lot of different application areas. So maybe I'll just hand over to Louis to do last words. Thank you very much. Thank the audience.
Yeah, I won't keep you here long, but I do have a couple of things to share with you. Does everyone enjoy the conference? Yeah? Not so much. All right, yeah. Thank you. Cool. So I appreciate the applause. And yeah, you should thank all the wonderful partners. Again, UCL School of Management has co-hosted, hosted, I should say, because they were the venue sponsors. So. But also Capital Enterprise co-organized Dataiku and pre-series Open Future AI Seat for the AI Startup Battle. A couple of more sponsors. I'm just trying to fill up while this. Yeah, there you go. So yeah, big round of applause to these guys as well. I've got this one that I need to give out to someone at some point. But before I do that, all right, watch your inbox in the next few days because you're going to get emails from me. Hopefully not too many, but at least one to notify you about videos being published on YouTube. You should be able to find them if you just search for PAPIs.io. Don't forget the .io, otherwise you could find weird stuff. Photos on Facebook, same thing, PAPIs.io. And slides, yeah. We intend to put all the slides from everyone to the same place, and then let you know about it when it's available. Hopefully, everyone will be happy with sharing their slides. Some of the talks that you've seen or that you've missed will be also turned into papers that will be published in Proceedings of Machine Learning Research. Watch your inbox. I'm not sure when that's going to happen. And in addition to our sponsors, I'd like to thank the program committee. There's quite a bunch of people, so I'm not sure I can say all of their names, but many thanks to them as they reviewed all of our proposals, rated them, helped us surface the best talks, and also recommended some good speakers. Many thanks to our session chairs who introduced speakers, moderated Q&A, so basically helped us run the events along with the team. and speakers, obviously, you've seen them, you've seen their names, but we've had quite a few volunteers also contribute to the event, so many thanks to them as well. And yeah, without them, I guess it would be very hard to run this event. So again, let's. Okay, almost there. Who won this thing? All right, so that's for the person who had the best tweet, or the tweet that got the most retweets, right? If I got that right. I'm just going to share that nice plot that Inigo from our team made. How can I zoom in? There you go. See? Data. And if you zoom in, the person who wins is Daniel Daniel O'Sullivan. That's you. Okay, there you go. We'll take a picture. And yeah, thanks to everyone else. Big Emma, Libby, Tom, me. See, I'm multitasked. All right, our next event is in Brazil. If you want to check it out, it'd be a pleasure to meet you in São Paulo. It's definitely worth it. A couple of months. And yeah, I want to take pictures. You're taking pictures, right? All right, I'd like to invite everyone who's been on stage at some point, everyone who's contributed to the event, both volunteers, session chairs, members of program committee, speakers. Let's try to fit everyone on stage and take a picture of all that crowd. Come on up.
You forgot to thank the most important people.
Probably wouldn't fit like that.
Okay, and from all of us, thank you for attending PAPIs. Thank you for being part of this conference. And yeah, very happy to have you here. Yeah, cool, thanks.